Now we've come to the third topic of the numerical methods lectures, namely the problem of solving ordinary differential equations. This will be the general introduction to that. So just a quick recap on what differential equations are. So differential equation is an equation that relates a function and its derivatives. So this is an example of such an equation where you have a first derivative of y with respect to x is going to be equal to some function of x. So this is a first order differential equation because we only have the first derivative. Almost all physical processes are governed by differential equations because in physics it means like a rate of change. So for example, here are some examples. So Newton's second law, the heat law, Fourier, and we have the diffusion, law of diffusion. So these are all examples of first order differential equations. Many differential equations cannot be solved analytically, and therefore they will require numerical methods to solve, to find a function. So we can classify differential equations into certain types, and I will be discussing ordinary differential equations, or ODEs. And these are differential equations that deal with functions of only one independent variable, as opposed to partial differential equations, where the function can depend on more than one variable. Besides this, you can also classify differential equations based on the boundary conditions that you are given. So on one hand, we have initial value problems, or IVPs, and here the conditions are specified at some value, at the same value of the independent variable. So often this will be at x, where t is 0. Alternatively, you have boundary value problems, where the boundary conditions are given at different values of this independent variable. And the focus of these videos on ordinary differential equations will be on methods to solve initial value problems, and I will be discussing the Runge-Kutta methods, and we have the first order Runge-Kutta methods, which is Euler's method that I will be discussing first. Then I will be discussing a slight improvement upon Euler's method, namely Hond's method, and then finally I will be going over the general form of the Runge-Kutta methods and the fourth order Runge-Kutta method, which is the most commonly used one. So just a quick preview on what the Runge-Kutta methods are. So the problem of ordinary differential equations is to find a function y of x such that this differential equation dy over dx is equal to some known function f of x and y. And again, we are discussing initial value problems, so you're given the value y at some initial value x naught, which is going to be equal to y naught. So for the Runge-Kutta methods, we can express this ordinary differential equation in this following way. So you can calculate the value y at a point xi plus 1, because it's equal to the value at the previous point, yi, plus some phi times the step size h. And here we can take phi to be an estimate of the slope of this function. So here in this figure you'll see a plot of x and y. So if we have a value of y, I, at some xi, we can estimate the slope and use it to estimate the value of y at a point further along the interval. And then you apply this formula repeatedly as to step by step trace out a trajectory of the solution. So to calculate it, a whole number of values for y. And all one-step methods follow this same principle, but they differ in the methods of estimating this slope phi.